another day of senior intermediate, and it's going to be on number theory. So the topics we're going to be covering today are number theory, prime numbers, the fundamental theorem of arithmetic, factors, and types of numbers. So our first section of today is number theory. And number theory is known as the queen of mathematics. And if you're wondering what this interesting picture is, it's a crown. I can't draw. Anyways, number theory is the study of positive whole numbers. And it also studies the relationships between different types of numbers, such as odd and even numbers, prime and composite, perfect cube and perfect square, modulo, and Fibonacci. So our second topic of today is prime numbers. And a prime number is a special type of number whose factors are only one and itself. And just a quick review, factors are anything that can divide a number that you have. So we have 25 prime numbers less than the number 100. So here they are: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. And there's something unique about these numbers is that there's only one even number, and that's 2. The reason that we don't have any other even numbers because an even number is even because it's divisible by 2. And 2 is the smallest even number, and its only factors are 1 and 2. So 1 and itself. Also, you only have one number that ends in 5 because a number divisible by 5 ends in 5 or 0. So you don't see any other numbers ending in 5 because, like I said, it would be divisible by 5, making it not prime. So those are some interesting patterns. So a composite number is any number that isn't prime. And the number 1 is special. It's neither prime nor composite. It's not prime because it has only one factor, 1, which is 1 and itself. But that's only one factor, so it really doesn't make sense. And it's not composite because it only has one factor, and composite numbers have more than 2 factors. So there's a way we can figure out if a number is prime or not. And what we do is we check for divisibility by primes less than the square root of n. So if I wanted to find if any number n was prime, I would take the square root of it and see if that is divisible by any number less than. Yeah. So now let's go over some of our divisibility rules. If it is even or ends in 0, 2, 4, 6, or 8, then it's divisible by 2. If the sum of the digits is divisible by 3, the entire number is divisible by 3. The last 2 digits are divisible by 4, the entire number is divisible by 4. If the number ends in 0 or 5, then it's divisible by 5. If it's divisible by both 2 and 3, then it's divisible by 6. If the last 3 digits are divisible by 8, then the entire number is divisible by 8. The sum of digits is divisible by 9, then the entire number is divisible by 9. If the number ends in 0, it's divisible by 10. And if you take the difference between alternating digits and you get 0 or the difference is divisible by 11, the entire number is divisible by 11. Our next topic is the fundamental theorem of arithmetic. And basically it says that every positive integer has its own unique prime factorization. And here's a tip for prime factorizing. Use a factor tree. For example, this is a factor tree. We have the number 48 and then we split it up into a prime number and the leftovers after you divide by that prime number. For example, your 48, it splits up into 2 and 24, then 2 and 12, then 2 and 6, then 2 and 3. And if you circle all our prime numbers to these 4 2's and this 3, you get your prime factorization, which is 2 times 2 times 2 times 2 times 3, or 2 to the 4th times 3. So our second to last topic is factors. So we have a bunch of formulas here, and I'm just going to go through them. So if we wanted to find the product of all the factors of the number n, we do n to the exponent of x over 2. And x in this case is the total number of factors that they have. So let's take a generic number, n, and let's say its prime factorization is 2 to the p times 3 to the q times 5 to the r times 7 to the s times and so on with more. If we wanted to find the number of factors, in general, we do p plus 1, which is the exponent of 2, q plus 1, which is q, r plus 1, which is 5, and s plus 1, which is 7, and so on. If we wanted to find the number of even factors, we're not going to add 1 to p, instead we're just going to multiply p times q plus 1 times r plus 1 times s plus 1. If we wanted to find the number of odd factors, we completely ignore the p and do q plus 1 times r plus 1 times s plus 1. So then we have the sum of all factors. So to find the sum, it's a bit confusing. So I'm going to do some examples. So first you're going to prime factorize, and then you're going to make a little geometric sequence, and then you're going to multiply. So basically what that means is, I'm going to, for this step, basically I'm going to find all the exponents of that number and add them up, and that's what I mean by geometric sequence. So let's just try an example because that's a bit confusing at first. So let's say we have the number 24. Its prime factorization is 2 to the 2 cubed times 3. So for the 2 to the cubed, I'm going to rewrite this as 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. I would write the 2 part all the way up to this exponent, starting from 0, going all the way to the exponent. And then for the 3, I do 3 to the 0 plus 3 to the 1, starting from 0, going all the way up to the exponent here, which is 1. But we don't have to write 1 because it's the same thing. So add these up. This is 1 plus 2 plus 4 plus 8, which is 15, and then 1 plus 3, which is 4, and then 15 times 4 is 60, and that's the sum of all the factors of 24. So let's try a bit of a harder one, 200. If we prime factorize 200, we get 2 to the 3rd times 5 squared. And if we do the same steps as before, we do 2 to the 0 plus 2 to the 1st plus 2 squared plus 2 cubed times 5 to the 1st plus 5 squared. So adding all these up, we get 15 like before, and 5 to the 1st is 5 plus 5 squared is 25. So 15 times 26 is 465, which is the sum of all the factors of 200. Our last topic of today is types of numbers. So we have 3 types of numbers. Perfect. So our first one is perfect. And this means that the factor sum equals twice the number. And some examples are 6, 28, and 496. Then we have our abundant numbers, which means that the factor sum is greater than twice the number. And it's 30, 40, 100, and all multiples of 6, excluding 6, because 6 is perfect. And then we have our deficient numbers, which you probably guessed was when the factor sum is less than twice the number. And examples of this are powers of 2, prime numbers, and 35. So our first problem of today is the following. Which of the following is a square number? Our options are in blue. 14 factorial times 15 factorial over 2, 15 factorial times 16 factorial over 2, 16 factorial times 17 factorial over 2, 17 factorial times 18 factorial over 2, 18 factorial times 19 factorial over 2. So basically, what we want to find is a square number. And we can have a square number if we have another square number times another square number, because together they also make a square number. You'll see what I mean in a second. So we can rewrite 14 factorial times 15 factorial as 14 factorial times 14 factorial times 15, because 15 factorial is basically 15 times 14 factorial. So we rewrite that as 14 factorial squared times 15 over 2. And we get 14 factorial over 2 times 7.5, which really doesn't work because this isn't a square number. Then we rewrite 15 factorial times 16 factorial as 15 factorial squared times 16, which gets divided by 2, which gives us 15 factorial squared times 8. 8 is a cube, but it's not a square, so we can't use it. Then we rewrite 16 factorial times 17 factorial over 2 as 16 factorial squared times 17 over 2. And we get 16 factorial squared times 8.5, which also doesn't work because 8.5 isn't a square. Then we have 17 factorial times 18 factorial over 2. We rewrite that as 17 factorial squared times 18 over 2. And we get 17 factorial squared times 9. 9 is a square. It's 3 squared. So basically, this square that we get is 17 factorial times 3 squared, which gives us this. Anyways, let's just go on, try this one just to be sure, because you always want to be sure. 18 factorial times 19 factorial over 2 gets rewritten as 18 factorial squared times 19 over 2, which gives us 18 factorial squared, I forgot to write 2, times 9.5, and 9.5 isn't squared, therefore our answer is D, 17 factorial times 18 factorial over 2. Our second problem is, what is the sum of the factors of 496? So the first step of doing this is we prime factorize it. We split 496 into 2 and 248, 2 and 125, 2 and 62, and 2 and 31. This gives us 4 2's, 2 to the 4th, and 131, which is 31. And we can't simplify it even further because 31 is prime. Anyways, now what we do is we write 2 to the 4th plus 2 to the 3rd plus 2 to the 2 squared plus 2 to the 1 plus 2 to the 0 times 31 to the 1st plus 31 to the 0. Then we simplify this and we get 16 plus 8 plus 4 plus 2 plus 1 times 31 plus 1, which gives us 31 times 32, which is 992. Therefore, the answer to the sum of the factors of 496 is 992. Our third and final problem is, for the number ABC, each distinct letter represents a different digit. If ABC, CAB, and BCA are all divisible by 6 and 9, what is ABC plus CAB plus BCA? So let's go back to our divisibility rules and let's think. So what's the divisibility rule for 6? The divisibility rule for 6 is that it's divisible by both 2 and 3, meaning that all 3 of our numbers have to be even. And for them to be even, C, B, and A all have to be divisible by 2 or even. So we know that A, B, and C are even. So we have that. And then to be divisible by 9, the sum of their digits have to be divisible by 9. So they can either add up to 9 or 18, because any more than that, they won't be able to reach it. And they have to add up to 18 because they're all even. The only way we'd be able to get to 9 if it's 2 are even and 1 is odd, or all of them are odd. But we want our sum to be, but our sum has to be 18. So to get 18, we're going to take our 3 largest even numbers, the even digits, 8, 6, and 4. 8 plus 6 is 14, plus another 4 is 18. So 864 or 864 is ABC. And then CAB would be 486, BCA would be 648, and they're asking us what is the sum of all 3 of these, and we get 1,998 as our answer. Don't forget to subscribe and like. If you have any questions, you can email info@agoramastercode.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!